like to thank the organizers. Thank you very much. Okay. So let me start by saying that this is something. It's a topic very fragile. So this will be quite my best. When we do statistical machine learning, we reason with models. We have a statistical model. Typically, there is an input space, an output space, a family of functions with some parameter in some space that can be small or large, and we try to fit the model using examples. Now, if you want to discuss research on these systems, in fact, there are basically 4 major questions. We must discuss the models, the approximation probability. You must discuss the loss functions, the asymptotic consistency, what they're going to do if you have plenty of examples. You must discuss the learning algorithms, how to optimize, what are the computational properties and everything. And you must discuss generalization, the impact of the finite training set, capacity control, and everything. And the big news is that this has been done, essentially. I say essentially because there are still things to do, but the important thing is that there are not going to be massive changes from this. And the message of this talk is that we should study a more complex object. I'm just going to outline this object now, and then I'm going to go through a lot of examples. We should use a collection of statistical models, and each one has different models, different things. Together with an algebraic structure that unites them, that basically connects the models and their realizations, and both aspects are important, and describes how to transfer knowledge across models. And the training data is completely unstructured. Each example could pertain to a particular model, test could be another model. The algebraic structure is the glue. And we need to focus on the glue because the glue is related to reasoning. So I'm going to try to present this in the order here. The first part is about auxiliary tasks and their role and what they do. The second and third parts are basically examples. The circuits, because it's not as simple and I'm using to see. And probabilistic models because they're connected. If I was doing it the other way around, you would wonder why I'm doing these things with probabilistic models. The fourth part is try to extend this to reasoning at large, and then some outlook. Auxiliary tasks. So I'm going to start with a problem that happened quite a while ago. You want to solve a big problem, a big machine learning problem, something like reading checks. So your inputs are images of checks. Your output is an amount, not even a string of characters, just an amount, a single number. And if you have examples of this, you cannot train it as a single model, or maybe you can, but it would require so many examples and so much computation that you can't really do it. So we go to, when we face such a problem, the natural answer is to use our engineering experience and engineer the machine learning system. So for instance, you can identify sub-problems. You want to locate the amount field, you want to segment the characters in the field, you want to recognize all of the characters, then translate the character string into an amount, and none of these problems is really trivial. So for each sub-problem you define a statistical model. It could be fairly complicated for the recognition models, or highly engineered and for the segmentation and location models, just a few adjustable parameters. And then you collect and label data for all these things. And lots of manual work, but manual labor is not too expensive in the end. And you train. Now, if you train, you actually have a lot of training strategies. The simplest one is independent training. You collect data for each sub-model, you train it. The second one that's a bit better is sequential training. You basically train the first model, which is the field location in that case. Then you run it, and you see examples of fields, and you label them as good or bad, and you train, so you label the fields by proposing segmentations with segments, then you train a segmented model, then you get segmented images, and then you train the recognizer, and you go on that way, in a sequential way. And when you do this, it's a bit better already. But then you can think, well, in my segmentation model, I have a lot of thresholds, and when I optimize the threshold, maybe I should optimize the threshold in order to maximize the performance of the whole system. And that takes you to the next idea, which is the global training. You pre-train the way you can, and then you take your data, your inputs, checking images, and the amounts. You consider all the submodels as a single thing, and you just train the multi-layer model. I will use deep model. So there are a lot of issues there. So, like the structure of the global model changes with the data, you have to manage hypotheses, you have to do things like that. And the composition of submodels can be non-trivial, like there is this label bias problem. But the big thing here is that we know how to do this. It's a lot of work, but we know how to do this. And we've done that for quite a while. So enters deep learning. So here's my simplified view of deep learning. I know it deserves a full workshop, but that's going to be enough. We pre-train with sequential and supervised training. We collect output of a submodel, and we train it in an unsupervised way. And then when it's done, we tune with some global training, and we look at the nice results, and we're happy. And that's very similar to what we did here, you know. It's very similar to applying the sequential training and then the global training tuning. The only difference is that in the engineered approach, all the tasks were understood as being part of the problem, like we engineer a big solution. While in deep learning, the tasks are very loose. You just unsupervise something, you put them together, and in the end you get something. So what I call the deep learning surprise is that, well, you don't need to carefully select the subtasks to be something that would make sense from an engineering point of view. Generic and supervised subtasks work quite well, and well, we don't need to have very expensive hand libraries. Just can do things quite easily. So in fact, engineering big learning systems is easier than we thought. Now, unsupervised, I'm just going to go here. Unsupervised learning, that's comparable to using really cheap labels. X1 and X2 are closed, X1 and X3 are not closed. They are not very interesting labels because we know that they're closed or not closed because we chose the input space to represent that. And this is what unsupervised learning does. So in the end, what we have is that we train with auxiliary tasks. If you think about the price of labels in various tasks, there are some interesting tasks. These are the ones we want to solve. And the labels are scarce, because if the labels were abundant and easy to obtain, the task wouldn't be that valuable. And you have tasks that are not so interesting. There are plenty of labels, like just saying these labels are closed when we know perfectly well that they're closed. And the idea is that in the vicinity of some interesting tasks, where the labels are there often are less interesting tasks with strict labels that we can put to good use. So unsupervised learning is just one of them, with trivial labels. So when you look at it this way, it's interesting because things like deep learning, or semi-supervised learning, or transfer learning, they become three facets of the same thing. And that's a good unification. It's good to see things that way. So let me give a few examples. So the first example, which I find quite enlightening, is a face recognition example that was proposed by Matt Miller in 2006. So our interesting problem is the following. We want to recognize the face of 1 million persons. And the question, of course, is how many labeled images per person will we get? Well, not so many. There is a related but less interesting problem. Are two face images representing the same person? And you can have lots of examples for that for very cheap. If you see two faces in the same picture, they're likely to be different persons. Okay, there are two exceptions. There are mirrors and twins. But you can somehow characterize that. If you see faces in successive frames, they're more likely to be the same person than faces in completely different movies. So in the end, you can build a system like this that takes two images, applies some pre-processing, the same one to extract some face features, and then the distance measures, it's going to say yes, no. Once you have this, you can just take this pre-processing, put it somewhere, add a classifier, train everything, and you get a classifier. And you know that by doing things like this, at least for faces, I don't know that for things like digits or characters, you know, adding a new class here is extremely easy because the pre-processing is already good. So another example which I could use to Ronan Colobert. The interesting problems are standard LLP tagging tasks. So Ronan has some demos, maybe you've seen that. And the related but less interesting problem is the following. We're going to say that the positive examples are legal sentence segments, or segments of legal sentences. And then we're going to perturbate it by substituting the central word, replacing it by something random. And we say it's a negative example, and use a ranking loss. So here is an example. You have a sentence, the cat sat on the mat, but you substitute a word by something crazy. Then you have the pre-processing layers that are going to represent each word in a certain space. And machinery that's going to say, this is good, this is not good. We want that when this is the original word, here, cat sat on the mat, this should give a high score. When this is random word, this should give a low score. Data for this is abundant. And Ronan trained on Wikipedia plus Brown plus a couple on 1 billion words. That's how that works. Then we take these pre-processing modules, you put them in some complicated machinery.
Did you say 1 billion or 1 billion?
Billion. Yes, 1 billion words. You put them on some machinery, you route the output of these modules into parts of speech, name entity, chunking, semantic programming, or even parsing. And you train that, and it works quite well. So, well, I didn't have the picture of the latest demo, but in that case, if you have something, I've made up this sentence to demonstrate Sena. So you see the various words here. You see the parts of speech tracks. You see the chunking. You see the name entity recognition. So it recognizes Sena, which is the name of the software, as a person, which means it's not self-aware yet. Probably not. But maybe. And for each of the verbs, you have a characterization of, for instance, for made, who made, the verb is being made up, made what, this sentence, and well, I don't know what PNC means, or maybe knows. And for demonstrate, you have who demonstrate is still me, and the verb is demonstrate, and what is Sena, and so on. And the thing works pretty quickly. Like, so what's interesting though is this. What kind of representations do we have here? And one way to look at it is to pick a word, look at the representation in that space, and look at what are the closest words in that space. And one I like is this reddish that is close to greenish, bluish, pinkish, purplish, brownish, grayish, whitish, silvery, and yellowish. And a couple others like that. So this space clearly captures something that's somewhere between syntax and semantic. So that takes me to my second part, circuits. This was an idea about auxiliary tasks and how they can be used. Basically, sort of viewing, semi-supervised learning, deep learning, and transfer learning through the same rules. So we have all these circuits, this is what I did in my previous examples. I took little models, or models that were composed of various modules, and I assembled them, I wired them in various ways, and I rewired them, and I do things like that. So what does it mean? First of all, for the training of these things, we can look at them with the Bayesian glasses. Suppose that this elementary module, this yellow and blue and green things, are parameterized by distributions. And step one, we train this auxiliary task. So it's not clear that the posteriors are going to factorize in 3 unique distributions, but there are techniques to project posteriors on the factorized space. So after training, I have a distribution here that represents this particular module, what it knows and what it doesn't know. I can plug it there, and what was the posterior here becomes the prior here. So it's a capacity control tool. We can play with the fact-based theorem and start to write nice theorems that tell you everything except what matters, which is that it doesn't say which transfer strategies are going to work best. Now, if I look more closely about the wiring, you can consider the wiring operation, when I take my modules and I wire them, as an algebraic operation. And what's interesting is that it operates simultaneously in two spaces. You compose the models, being a function that's parameterized, and you also compose the model realizations, which is the model's one strength. And so we transport both the functions and their parameterization. And that induces another algebraic structure on the parameter space that's necessary in order to make sure that the statistical models match their realizations. But this is a complicated way to say that when you take two models with two different sets of parameters, the global set of parameters is the concatenation of the parameters of both, and that you can have parameter sharing and things like that. And more interestingly, it inherits, there is an inherited structure in the space of questions of interest. So in that case, it means that each of these models, like for instance, this thing here, C as a whole, is a model that takes as input two images and outputs a decision about representing whether there is a same person or not. So that's a question of interest. Not so interesting, but a question of interest. This one is a question of different nature. Take an image, say who is in the image. That's a different question. And by rewriting my module, I also connect the various questions. So basically, this algebraic structure is an expression of the semantic. And in fact, this circuit algebra is pretty much the same as the semantic equation models that were described in Perl 2000 in the causality book. And so, in terms of semantics, this algebraic structure, the circuit, is more causal than correlations. And because it's oriented, if you have correlations, they're symmetrical. When you have modules that have an input and output that you connect, it's oriented one way or another, they're not the same. So, because the algebraic structure is a reflection of the semantics, well, we can enrich the semantics by enriching the algebraic structure. And a good way, that's time-honored to enrich an algebraic structure, is to make it recursive. So let's do that. In fact, this has been done long ago. This has been done by Jordan Pollack in '88 with the recursive auto-associative memories. And Jeff Hinton had the paper that was mapping parts and whole, connecting part and whole. At the same time, there was the same kind of ideas. So the elements are a representation space. I don't say what it is. It doesn't matter what it is. The only thing that matters are the algebraic properties. There is an association module that takes two representation vectors, the two vectors, and produces only one. And this association module takes one representation vector and produces two. And it's supposed to be the opposite of the other ones. There is an invariance. We want that the dissociation of the association reconstruct the input. So for instance, we can take two words, the cat, map them into some representation space, associate them to have a representation of the complex the cat, and dissociate it to get the cat. And then if you have something more complicated, sat on the map, associate it in various ways, dissociate it in various ways, and reconstruct the sentence. Now the important thing is that now you have a tool to navigate the sentence. If you build this representation here, you can apply the dissociation module to split it between the verb and the complement, and go down, go up. Basically, this is, what did I say? So, if you have one of these recursive auto-associative memories, it can represent an infinite depth predicate. If fit exact. It's the same as the list operator of Kahn's CDR, except that the representation space could be anything. Now, of course, if the representative space is just a numerical thing like a vector in R100, there are going to be numerical accuracy issues. When you're going to start to do things too deep and reconstruct, you're going to lose something. So you're going to reconstruct something that's not exactly what you had at the beginning. And the claim is that if the embedding in the representation space makes sense, the dissociation module will reconstruct approximate sentences. Something very human, in fact. When something too long a sentence or too complicated a hierarchy is something we can't remember, but when we reconstruct it, we reconstruct something that's similar. So now let's look how you take a sentence and split it or something and associate it in various places. And there is a mechanism that I call the Universal Parser. It requires two other things. It requires a module that I call the saliency score, the saliency module producer score, and that's going to tell me whether the representation here is a good one or not. And by a good one or not, it means are these two objects that I'm associating objects that often appear together or not. And it requires a short-term memory. So to parse pretty much anything, whether it's a text or an image or whatever, you have two operations to schedule. The first one is taking an input, putting in short-term memory. The second one is taking two representation vectors from the short-term memory, associate them, and putting them back here. And the question is how to schedule and how to choose which two. And it's simple. We want to get a very high saliency score overall. So there are various approximations to do that. If you consider that these are the stack form, you get a stack parser. But anyway, now the interesting thing with this model is that it's related to the idea of chunking. You all heard about this 5 plus or minus 2 concept that we can remember 5 plus or minus 2, but 5 plus minus 2 what?
7 plus.
7 plus minus 2? Yes. I forgot, I'm sorry. So the question is what? And in the literature they describe this as chunks, things that go well together. And this is what this thing does. Now it comes to the question of training these things. So we have first the supervised training, and I think Richard Socha has plenty of examples of that. So I'm not going to show that. Basically it works. So unsupervised training now. Well, we can do it exactly in the same spirit as the Colobert example on Wikipedia. Suppose you take a correct segment of a sentence, start on the mat. You associate it using the parser in the way you consider good. You apply the saliency code, everything good. Now you can replace one word by something crazy. And so this link is wrong. And some of these links are wrong. And you have scores that you should expect to be bad, because these things should not associate together. Once you have this, you define the ranking loss. You try and you get something. What kind of a something? Well, actually, we did that long ago during an intern. Vincent Etter was an intern in Nice, and we were supervised by Renan and do that. So, Wikipedia dataset. Vocabulary restricted to just 1,000 words because we want to start small. All pairs of the 500 most frequent words were mapped into the representation space, which in this case was just a 50-dimensional vector. So, if you take the point in this space that represents the city, and you look at the points A1 that represents the closest pairs of words, all possible pairs of words, you get the town, the church, the village, the state, the country. 2 men, 3 men, 4 men, 2 children, 2 women, 3 children, and so on. So the first remark is that it looks quite good. The second remark is that it's awfully syntactic. 3 men and 4 men is not the same thing, you know, and the red house and the German house is not the same thing. It's the same category of thing. And the reason why it's not the semantic is exactly what Raymond said this morning. It's not grounded. There is no grounding gap. And you can keep enriching the circuit semantics. You can add more things. So one thing that's interesting is to go towards natural language understanding. And there is this. So we want to deal with semantics. We want to deal with understanding. And in natural language processing, well, it's dominated by the minimal program of Chomsky, which is to say, let's forget about the semantic for now. It's too complicated. Let's look at the syntax and how much of the syntax is needed to actually be able to carry semantics. And let's do parsing, let's do things like that. But in fact, there were currents before that, in particular the structural linguistics, and in particular Zelig Harris in the 60s. And they invented this thing called operator grammars. So if you look at the parse tree, it's a structure within the sentence. What Harris was doing was considering the space of all the sentences and considering operators between sentences, transformations. You can transform a sentence into another sentence by a very mechanical operation, but also as an associated semantic. You can move a sentence in the past, you can add an extra term that's going to give, let's say, a manner, or that's going to add new things. And so, this operator grammar is very similar, it operates in the representation space, which is the space of all the sentence, and has some algebraic structure that represents English. And there is a book where it describes all the operators you need to describe English in this view. You could do that in that space. As long as you have the right algebraic structure, you can do the thing. Of course, the numerics are going to haunt you, and so if it's too deep or if the sentences are too complex, you're not going to be exact, but that's very human. You can also go towards first-order logic. Like you can add specialized modules for variable bindings and quantifiers. The connectionist approach, like Spolensky in the 90s, and you can do that by having modules that do instantiation, so replacing a variable by its value, or replacing the subtree by a variable, and manipulate your representations that way. It's complex. You have alternative ideas which are closer to language, like having modules, boxes, that do things like anaphora resolution. Which tree nodes represent the same entity? Or do what I call restricted entailment. Is this tree an instance of this other tree, which is a way to have this kind of relation between the representations. In fact, you can play in this representation space in many, many ways. So that takes us to, actually, we're going to put this on hold and start looking at probabilistic models. In NIPS, there are plenty of probabilistic models. It's a big part of what we do. And therefore, it's important to understand how they're related to these kind of ideas. So, first of all, why are probabilistic models appealing? And there are clearly two visions of machine learning. There is what I call Vapnik's razor. When solving a problem of interest, do not solve the more general problem as an intermediate step. If you want to classify patterns, use a pure classifier like SVM. A pure classifier outputs a class, just a class, only that, not even a score, if you switch. But we might want something more complex, which means that we should not solve a more general problem as an intermediate step, but we should be sure that we will not solve a problem that's simpler than what we want. Now, if you use probabilistic models, you can easily handle variants of the problem of interest. Like for instance, in speech, you can have an acoustic model, which is probabilistic, a language model is probabilistic, plug them together with Bayes' rule, and have a speech recognition system that's going to do something. And the probability theory has an important supporting role because it describes how to manipulate probabilities, and together with a semantic interpretation of what it means to combine probabilities. It connects well with our way to do things. So let's look at the graphical models, of whether directed or undirected. You can look at this with the algebraic glasses. You can consider the family of all conditional distributions in variables. For instance, P of x2 given x1 and x4, P of x2 given x3, x4, all of them. All the P of any variable given any other variable, possibly not. And you have algebraic operations that connect them, like marginalization and base rule. The operators that operate on these conditional distributions and allows us to get some of them on the basis of others. This operates on the model realizations, because I speak about probability, I didn't speak about the parameterization at all. Now, of course, we have independence assumptions. Basically, we restrict the family by saying that P of x3 given x1, x2 is actually the same as P of x3, x1. That's an independence. And that facilitates inference. Okay, of course, we have that. Now, what about the parameterization? And I think this sentence is from Heckermann. This is all about the parameters. So in a graphical model, the parameterization is often implicit. The probability theory induces an algebraic structure on the model realization, not the models. But in fact, if you look, people have devised languages to describe the parameterization. And if you have such a language, you have something very similar to the circuit. You have a class of model, a family of statistical models, and an algebraic glue that connects both the models and their realizations. Examples. Sometimes people use plates to make the parameters explicit. Like for instance, you have this CV model, which is x is the input, y is the output, y is conditioned by x. If you write it that way, you say nothing about the parameterization. You can also write it this way, where you make the examples explicit in parameters explicit. And that's the way you should write it if you're really a Bayesian. Because when you see it that way, and you apply inference in that graph, it tells you how to use base rule to recover the parameters, the distribution, and everything. But there are other languages, like for instance in probabilistic relational models or relational dependency networks. These are languages that defines a base net that encompasses all the examples. Like there is a nice example that comes from Levin and Jensen in IMDb, which is about predicting the receipts of some movie. And we have a graph, the IMDb graph of the movies with the actors and the actors played in which movies and so on. And what the system is doing is that it creates a base net of all this structure with shared parameters. The movies, the local piece that describes this movie is the same in parameters, as the same parameters, share parameters with the local piece that describes other movies. So when you extend with new movies or new things, you basically have a model that's clear. So another one are Markov logic networks. And this time we generate a base net and a parameterization using a first order knowledge base.
Markov.
Markov logic MNNs?
Bayesian logic programs generate Bayes nets. Markov logic networks generate Markov net on direction model.
Yeah, okay, but sorry, I'm not. I don't make a difference. No, so the semantics of these are just same as circuits. You have an algebraic structure on the space of models and realizations. It induces an equivalent structure on the space of questions of interest. And this language that defines the connection. So what I would like to, the point I would like to make here is that in the actual use of graphical models, or probabilistic models, people had to invent extra languages that describe this connection. How to not only connect the realizations using probability theory, but also connect the models. So if I compare circuits versus probabilistic models, there are common aspects, a family of statistical models, algebraic operation that works in two spaces, the space of statistical models and the space of realization, with their inherited structure in parameter space and the place of question of interest. Just the algebraic structures are different. Like probabilistic models, well, that could be like Bayesian nets, like PERL and T8, and the circuit algebra that closer to the semantic equation models, like PERL 2000. And of course, PERL 2000 has to be better than PERL. So I couldn't resist. It's not clear. Then I'm trying to make this into a more general source, which is where I'm starting to have problems. So, here is a possible definition of reasoning. Algebraically manipulating previously acquired knowledge in order to answer a big question. It's too general. It's too general because it includes logic reasoning, but also probabilistic inference, also circuit manipulations, also sample transfer learning, and well, there is this idea that there might be a continuum of reasoning models. You know, when we see a scene, we just know what it means. When we hear a sentence, we know what it means. Now, we are able to reason formally about a scene or a sentence, but nothing proves that the formal process happens before we ask for one. So, okay, reasoning model, the same thing basically. Remark, this suggests that reasoning models are arbitrary. Examples, well, there are numerous examples of reasoning. The logic reasoning with logical clauses. This is what people call reasoning most of the time. Probabilistic reasoning about correlations, causal reasoning about interventions. If I do this, is going to happen. And a good example is the Newtonian mechanic. It's actually quite interesting. You have various problems that go from having point masses or pendulum or something like that. Another problem, which is trying to describe the orbit of a planet around the sun. And they're connected because you consider that you can transfer information from one to the next. If you measure a gravitational constant on a small, you hope that you can measure a gravitational that is going to work on the big. And the way it works is by introducing an abstract concept, the forces, and an ensemble of laws that describes how to manipulate them. In particular, and this is why it's causal, it also describes how you can intervene on a system. When you intervene on a system, you do it by applying a force, or by putting a geometrical obstacle, which is a form of a force as well. There is the visual reasoning business. So for instance, if I change a viewpoint and move from here to here, I see a different part of the same scene. But this can be seen as two different models, and the ensemble of what you see in different viewpoints are connected with some algebraical relation that will create a 3D dimension. And then you can become crazy and see, well, social reasoning, it's about maybe trying to understand something from the point of view of the other person. And there are also less convincing examples of reasoning models like astrology, mythology. Astrology is a complicated reasoning where you try to understand the future using the planets. But on the surface, it has the form of a reasoning. Maybe it's not very good. Maybe it doesn't have a very high predictive value. But it has the form of a reasoning. So this multiplicity gives a lot of opportunities. Like in reasoning inference, there is always a tractability problem, and that's been a recurrent problem, whether in logic or probabilistic. And should we use universal reasoning models with all the computational issues, or should we tailor them to our application? Maybe working around computational issues. Like for instance, if you compare the circuits and probabilistic models, in probabilistic models, many forms of inference can be incomplete, it wasn't done all. In the circuits, they're all trivial. You just plug the circuits together. And there are a lot of open questions. How do we classify reasoning models? Characterize their predictive abilities. We don't want to do astrology, we want to do something that works. Characterizing their computational aspects. And another one which actually bothers me is that I can see three ways to reach first order logic. You can do it like Markov logic networks. So basically, you give one model per fully instantiated clause that gives the truth value of that clause, and you put them together with something. You can lift them in the quantifiers. So you can have functions that are going for each clause to give its truth value as a function of the free variables, or the universally quantified variables. Or you can do it with the circuit trick and the representation space. So we have a circuit association dissociation that provides a way to define predicates and expressions, and instantiation you have to get the machinery. And the first two, they're quite close. The third one is radically different because it also contains a way to represent its own expressions. So when I said before that when we see a scene or we hear a sentence, we know what they mean, but if asked, we can certainly provide a formal description of the scene, Well, the last one maybe has the tools to do that, because it has a way to represent the formal description. But the difference between these things I don't really understand, I'm sorry. And Outlook. So in this presentation, that's maybe I'm reasonably ambitious and I hope not too vague. So what we did is revisiting the story of auxiliary tasks, review circuit approaches to transfer learning, see that they can be you can enrich them to increase their semantic reach, look at probabilistic approaches to inference and point out similarities between circuits and probabilities, as well as differences, and try to conceptualize reasoning models. So why to do that? Well, these days, lots of ideas seem to fall in place. I became very excited about all of this. I'm pretty convinced that we can build interesting natural language processing and vision systems. And the question is, can we understand them really deeply and what they do? And I think we won't unless we answer these kind of questions. Well, that's it.